So what I'm going to demonstrate here is, especially for these lower cost SDRs like the FTR dongle, why you need a FM trap, or how well an FM trap works. And basically, this here's SDR Sharp showing a couple of FM stations. You can hear it going on in the background. And here's a quick look at the setup. This is the SDR with the up converter in its box, which I've demonstrated earlier. Antenna switch. Here's the FM trap filter, and then here's a signal splitter. And basically this is just a jumper to let the full signal path go through, and then we have the filter over here. And this FM trap filter, basically what I did is I took two of these FM traps here from MCM Electronics. They'll attenuate the FM signal 20 to 30 decibels a piece. And I've taken two of these out of their original packaging and put it in this filter box here for a setup like this. They're ganged together, and they'll provide 35 or more decibels of attenuation of the signal compared to one of them alone. And the reason for this, which I'll show in a little bit, is that I'm about 6.3 miles, 10.1 kilometers from multiple FM stations. Now I'm going to demonstrate how the filter works. Right now you're looking at several different FM signals. There's one here, here. They're pretty strong stations. I believe these two stations here are 100 kilowatts FM stations. And you'll get to see how the filter works. Right now the peak of these is coming in minus 30 decibels here, minus 25 on this one here. And when I put the filter in, the signal drops down quickly to the background, which is minus 60. So right now I'm getting 35 to 40 decibels of attenuation minimum on these with this filter in. So you can see it works pretty well. And then next I'll show you how close all these stations are to my house. But you really need it, otherwise you get intermod all over the place in all the different frequency ranges. If you're trying to listen to high frequency or other frequencies, you're going to get some kind of intermod from these powerful FM stations. So this is basically the reason why I need to put these filters in. Now you look here, my QTH is right over about here, and here's several stations up on a mountain over here in Golden, 6.3 miles, 10.1 kilometers away. Well, that's not too many. There's two or three over there, there's one down there. But when you expand it out, you see there's quite a few more. And like I said earlier, these stations range anywhere from about 20 kilowatts to 100 kilowatt FM stations. So when you take all that and factor it in, you can see why there's so much overload in the system there. So you can see how close the stations are to my house, and there's a whole bunch of them, and there's just so much RF signal coming in from all those that you get intermod all over the place. And that's one of the problems with the low-end RTL 2832 dongles. They just have a really wide open front end, and they're very susceptible to intermod. Filter in. And filter out.
With the new Boost mobile phone, just think of all the Friday night plans you won't be missing out on. Special someones that will be swiping right on your...
Okay, so here, like with the FM demonstration, I'm going to show you, with the FM trap demonstration, I'm going to show you why you might need a high frequency, high pass, basically letting everything above 1.8 megahertz in, but keeping the AM out. The AM, since much like the FM, a lot of strong local stations nearby. This here is the upper end of the AM band. Each one of these spikes is an individual station. Right here 760, and this one up here is 1690. And I think I'm on 1430. As you can see, it's coming in pretty strong. Bunch of stations coming in. And over here, this is actually some intermod. You think, oh, well, that's some strong signals there. When I put the filter in, you see all those stations go down, including the intermod here. It doesn't take all the AM out. I think it takes it down about 30-40 decibels, but it does take most of it out. So for right now, that's the 1430 station, and then if we come over here, this is showing up as about 2.67 megahertz, but this is actually KHOW intermod from that. Here's a different one here, not coming in as well, but definitely some intermod from the AM. And back to there, local station. We'll turn this off, and we can see that it takes it down roughly, let's see, the highest ones here are minus 10, minus 7 decibels, and it brings the spike here of this one down here to minus, about minus 50. So that's more than 40 decibels attenuating it. So the filter test setup is pretty much the same as last time. I have the SDR with the up converter here in this box. The up converter is in because we're listening to the AM for the demonstration. Here's the antenna switch to switch back and forth from the filter and the jumper. The jumper lets through the full signal. This is the high frequency high pass filter. And then we have the antenna signal splitter here. And basically the high pass filter consists of 7th order Carroll elliptical that I designed using LC. You can see it's a lot of capacitors and some transformers in there. But basically that is giving me 40 plus decibels of attenuation in the AM band when I put the filter in. And then I'll show you some of the upper frequencies on the higher band to show you kind of what the filter insertion itself might do. Okay, so here's an example of 2.5 megahertz time signal. You can see it's right there. There's the time signal. These are actually spikes from intermod, even with the filter in, because I had to amplify the signal 25 or 30 decibels to get it in. But here's the time signal. Here's the minute announcement coming up about. Okay, so that's with the filter in. If I take the filter out with the amplification that I need to hear it, even though I'm 40-50 miles away, I'm only getting ground wave, you don't get anything. Not at all. All this is intermod from the AM band. So that's the 2.5 megahertz signal. If I put go up here, we do 5.0. We do the same thing. There's the 5 megahertz signal coming in. That's actually coming in a little bit better, and that's with the high frequency high pass filter in. Without, you can see that the noise is appreciably higher. It's not quite as bad in the 2 megahertz region, but you can see it's quite a bit worse with the filter out. And the filter back in, signal to noise ratio is a lot higher. So here's the weather band. The filter's out, and when I put the filter in, the slight jolt was when it was in between the two different antenna sources, but there's very little insertion loss, probably 3 decibels or so. It's kind of hard to tell because the signal bounces around. So here's an example of the filter parameters I created in LC. I haven't swept the filter to see how accurate it follows the theoretical example, but you can kind of get an idea. Here's the minus 3 decibel points right at 1.8 megahertz, and then below 1.8 megahertz it's a minimum of 40 decibels drop. And we saw that when we used the AM band as an example and turned the filter on and off, and it dropped at least 40 decibels in some of the signals seen.